Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are starting our deep dive into Unit 14, which is Semiconductor Electronics. Our mission is simple: to make the introduction so clear that you lose any fear you might have and are perfectly ready for your exams. So let's start with a very basic question. Imagine we need current to flow in a device. If we want maximum current, we just use pure copper, right? An excellent conductor.
Of course.
And if we want zero current, we use rubber, a perfect insulator. So my question is, why do we deliberately choose something in the middle? Why use a semiconductor at all?
That's a good point. It does seem a bit counterintuitive. Why would you build high-tech electronics with a material that's only mediocre at conducting electricity?
Exactly. And that confusion is the key. Let's look at how semiconductors break the rules we know from metals. Think about a copper wire. What happens to its resistance when you heat it up?
The resistance increases, the atoms vibrate more and get in the way of the electrons.
Correct. Standard behavior. But a semiconductor? It does the exact opposite. Heating a semiconductor actually increases its conductivity.
Wait, what? Really? How is that possible? That's completely different from any metal.
It's because in a metal, all the charge carriers, the electrons, are already free. Heat just adds noise. But in a semiconductor, the electrons are initially locked in their bonds. The heat gives them the energy to break free, so you're actually creating more charge carriers.
So temperature isn't just noise, it's like the key in the ignition. It's what gets the whole thing started.
Precisely. And this unique tunable property is why your phone can even charge. Think about your phone charger, that little black adapter. It takes the AC current from the wall socket.
And has to convert it to DC for the battery.
Exactly. And it does that job using semiconductor devices called diodes. They act like a one-way valve for electricity.
So copper could never do that. It just lets the current flow freely in any direction.
Right. Diodes provide control. And this brings us to the core idea. A semiconductor is not defined by its intermediate conductivity. It's defined by the fact that its conductivity can be precisely controlled. It's like a valve for electricity. To really get this, let's use a highway analogy. A conductor, like copper, is a wide open highway. New toll booths, no signals, cars just flow.
And an insulator is a completely blocked road, a dead end.
Perfect. So the semiconductor is a highway where we can install toll booths, signals, and ramps. We can control the flow of traffic.
But why would we want to control it? Why not just have the free flow of the copper highway?
That's a brilliant doubt. The why is because we need to do more than just let current flow. We need to switch it, amplify it, direct it. Before semiconductors, the only way to do this was with vacuum tubes.
I've seen pictures of those. They look like big old-fashioned light bulbs.
They were, and they were terrible. They needed hundreds of volts to run, they got incredibly hot, and they were huge and unreliable.
So we needed a solid-state solution, something small and efficient.
Exactly. The invention of the transistor in 1948, based on semiconductor physics, solved all those problems. It was a revolution. Now, let's visualize how this control works at an atomic level. Picture the crystal structure of pure silicon. Every atom is bonded to 4 neighbors. All its valence electrons are locked in place.
Okay, so in its pure form, it's pretty much an insulator. No free electrons.
Right, that's called an intrinsic semiconductor. Now comes the magic: doping. We add a tiny bit of impurity. Let's say we add phosphorus, which has 5 valence electrons.
But silicon only has space for 4 bonds.
Correct, so that 5th electron is just left over. It's a free negative charge carrier. This creates what we call an N-type semiconductor. N for negative.
So we've intentionally created a loose cannon, an electron ready to move.
It's like a loose ball ready to roll.
Yeah.
Now, what if we added impurity with only 3 valence electrons, like boron?
Then there would be a missing electron in one of the bonds, a vacancy.
And that vacancy is what we call a hole. We treat it like a positive charge. This is a P-type semiconductor, P for positive.
Okay, so the hole is like an empty chair that another electron can jump into.
Exactly. And when an electron moves to fill the hole effectively moves in the opposite direction. That movement of holes is a real current. The real power comes when you join a piece of P-type and N-type material. That forms a p-n junction, which is the control barrier that is the basis for almost all electronic devices.
Okay, so now that we have the concept, let us see how NSERT formally classifies these materials for the exam. It's all based on resistivity, rho, or its inverse conductivity, sigma. Could you read out the formal definitions for us?
Of course. According to NSERT, solids are broadly classified as 1. Metals. They have very low resistivity in the range of 10 to the power minus 2 to 10 to the power minus 8 ohm meters. 2. Semiconductors. They have intermediate resistivity. And 3. Insulators. They have very high resistivity from 10 to the power 11 to 10 to the power 19 ohms.
Right. Just look at those numbers. The difference between a good conductor and an insulator is just massive. It spans more than 20 orders of magnitude. That range is hard to even imagine. Is there a simpler, more conceptual way to understand why the difference is so huge?
Absolutely. We use the energy band theory for that. It's the real physics behind those numbers. When atoms come together to form a solid, their electron energy levels merge into bands. We only care about two of them. The valence band, where electrons are locked in bonds, and the conduction band, which is higher up.
And an electron has to get to the conduction band to be free and carry current.
Precisely. The gap between these two bands is called the energy band gap, or EG.
So this gap must be the key.
It is. In metals, the valence and conduction bands overlap. The gap is zero. Electrons are already free.
So they conduct electricity easily.
Yes. In insulators, the band gap is huge. More than 3 electron volts. It's like a massive wall an electron can't climb. So no conduction.
Okay, so semiconductors must be in the middle.
Exactly. For them, the band gap is small, less than 3 electron volts. For silicon, it's about 1.1 eV. This gap is small enough that even the heat at room temperature can give some electrons enough energy to jump across.
Ah, so that's why heating a semiconductor increases conductivity. The heat helps more electrons jump the gap.
You've got it. That small, manageable gap is the secret to everything. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now let's really see the power of doping in action with a simple example. This is where the numbers get, well, staggering. We said pure intrinsic silicon is almost an insulator. Its resistivity is very high, about 2.3 into 10 to the power 5 ohms.
Okay, so it's a very poor conductor on its own.
Very poor. But now we add a tiny amount of phosphorus impurity. And I mean tiny, maybe 1 atom for every million silicon atoms. After we do this, the new resistivity of the material drops dramatically. It becomes 0.01 ohms.
Wow. From 230,000 down to 0.01, that's an incredible change.
It is. If you calculate the change in conductivity, it's the inverse of resistivity. The conductivity increases by a factor of about 2.3 into 10 to the power 7.
Let me just process that. That's 23 million.
Yes. Adding a tiny controlled pinch of impurity made the material 23 million times more conductive.
So that's the real power. It's not that it's a semiconductor, it's that it is a controllable conductor on a massive scale.
That is the single most important idea. This ability to dial the conductivity up or down is the foundation for the next chapters. It's how we build PN junctions, diodes, and transistors. Now, let's move on to the silent killers. These are the common misconceptions that can cause you to lose marks in the exam.
Okay, the conceptual traps.
First one. Many students think semiconductor means weak conductor because of the name.
Yeah, that it's just halfway between copper and rubber.
Right. But that's wrong. A semiconductor's defining feature is controllable conductivity. Pure silicon is nearly an insulator. Its usefulness comes from our ability to engineer it.
So the key is not that its conductivity is moderate, but that it's tunable. The 23 million factor proves that.
Exactly. Remember, semiconductor equals controllable conductivity. Misconception, too. Students assume heating a semiconductor decreases its conductivity, just like a metal.
Because that's our everyday experience with wires and circuits.
True, but the physics is different. Here, heating creates more charge carriers by breaking bonds. This effect is much stronger than the increased resistance from vibrations.
Okay, so for semiconductors, hotter means more conductive. It's the opposite of metals.
Perfect. And the last one. Many think only electrons carry current and that holes are just empty space.
Well, a hole isn't a physical particle, so it's easy to dismiss it.
But you can't. The movement of a hole is the collective movement of many electrons, and it constitutes a real current, especially in p-type materials. We have to treat holes as real positive charge carriers.
So holes are real current carriers, just moving opposite to electrons.
You have it. Now, to help all this stick, let's use some memory anchors. First, a simple phrase to remember the whole story. Pure equals insulator-like. Doped equals controllable. Junctions equal devices.
That's nice and simple.
Then there's a mnemonic, NICE, to remember the types. N is for N-type, which has donor impurities and electrons as majority carriers. I is for intrinsic, with equal numbers of carriers. C is for conduction, which is about charge movement. And E is for extrinsic, like P-type, which uses acceptor impurities and has holes.
I see. Okay, I'll remember that.
And finally, a physical gesture. When you think of doping, I want you to mime turning a dial with your hand. You are literally turning up the conductivity dial, and you can turn it up 23 million times. That's the control you have. All right, let's wrap this up with a 3-point exam-safe summary. 1. Semiconductors are vital because their conductivity can be precisely controlled, unlike fixed conductors or insulators.
2. This control comes from their small energy band gap, which is less than 3 electron volts, allowing doping or heat to create mobile charge carriers.
And 3. Doping, adding impurities in parts per million, is the key technique to create semiconductors with high engineered conductivity, which is the basis for all devices like diodes and transistors. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Study well, and we will see you in the next Concept Explainer.